Welcome back. In the previous class I was talking about the stability theory of the discrete nonlinear systems and what was our observation. So, approximately whatever theory that is developed for the continuous time nonlinear system, that is extended for the discrete time systems, and in place of exponential stability just people are talking about the geometrical stability. Okay. In this lecture, with help of whatever previous stability theory we have discussed, we are going to propose some kind of new kind of sliding mode control, that is called discrete sliding mode control. So far we have just discussed about the continuous sliding mode control. In this class we are assuming that our system is inherently discrete and then how to develop sliding mode control for that particular class of system. So what is purpose of discussion? Main purpose of discussion is why we need discrete sliding mode control. So if you see the literature, so there are several practical systems where control is implemented with help of the digital computer or macro controller, and we know that digital computer and macro controller are only compatible with the discrete time signal, and due to that reason in this way I can able to justify the requirement of the discrete sliding mode control. Most of time whenever we are assuming continuous time system, particularly if you talk about the sliding mode control, so we are assuming that due to the discontinuous term, so control is changing with very high switching frequency. Okay. But whatever our system, every system has some kind of inertia, some kind of delay, and due to that reason performance of the continuous time system or whatever theory we are developing for continuous time system, that is not compatible, particularly during the practical implementation. And digital implementation of continuous control, so basic philosophy that you can develop theory for continuous time system, and after that you can apply the sample and hold, or in another way we are first discretize the continuous control and using sample and hold I am going to implement it to the practical system. But in this particular process, particularly for the sliding mode control, unwanted chattering kind of phenomena comes into picture, and in this way the one of the key feature, that is robustness of the sliding mode control. So we are going to compromise with the robustness as well as stability of the overall system. So what is practical advantage of discrete sliding mode control over the continuous one? So now first discussing before the discrete sliding mode control, I am going to tell you how basically people are designing discrete sliding mode control. First they are creating the continuous mathematical model, and after that they are not discretizing the continuous control, but they discretize the mathematical model. Okay, and no mathematical model is exact, and due to that reason we know that after discretization obviously whatever model we are getting, that is not perfect also. Now for that imperfect discrete model we are going to design the sliding mode control, and due to that reason name discrete sliding mode control comes into picture. And whenever we are going to do that kind of task, so basically lower switching frequency requirement comes into picture, okay, than the continuous one. And these kind of system, there are several classes of system which is inherently discrete in nature, okay, and even if that is not discrete in nature, but whenever we are designing control, one of the important factor that we have to get measurement using sensors, okay, and most of time in order to get next instant we have to wait for again next output, and due to that reason control whenever we are going to update the control, since information is still not arrived, and due to that reason we have to wait. Okay, suppose that I have to control some kind of satellite and we have ground station. So whatever, whenever some information we are going to send the satellite and again that will come back, in this particular process always there are some kind of lagging of time. Okay, even if whatever satellite system that is continuous in nature. Okay, and due to that reason this will just justify the practical utility of the discrete sliding mode control. And obviously one issue is the computer control system, because nowadays whatever things we are trying to implement, so we are trying to implement using some kind of network, and where role of the computer is very, very important. Okay, and due to that reason we need some kind of methodology such that even if I will develop theory for continuous time system, that is implementable in discrete framework. Okay, and there are several system which has sampled measurement, that for example biological system, radar, economics. Okay, and obviously power electronic systems, where basically we have to control the on off operation. Okay, and at that time again it is possible to show that discrete sliding mode control is more justified. So what is key benefit if we will switch from the continuous sliding mode to discrete sliding mode? Obviously one of the main prospect is the implementation, because you can develop any kind of theory, but if implementation that is not good, give us good performance, so that theory is not so useful. And due to that reason practical applicability of any theory is very, very important. And obviously we have limitation, always theory will develop very fastly, but if you see the progress in hardware, so that is very, very slow, and due to that reason always some lag between theoretical development and practical development comes into picture. So using some new methodology, somehow we have to compensate that kind of mismatch. Okay, and due to that reason we are going to propose the discrete sliding mode control, and using this particular discrete sliding mode control, implementation of the digital control in modern system is basically easier. So if you see history of the discrete sliding mode control, so obviously variable structure control is developed by Professor Emelianov and Professor Utkin, and after that again the variable structure control, discrete variable structure control comes into picture, and their route of development is again lie in the same country. Okay, and term discrete sliding mode control is introduced by the Professor Utkin and Darkunov. So Professor Utkin is one of the founder of the sliding mode control. Several times I have repeated that, and after that you can able to see that several people has contributed in this particular direction. So I have just given the few names. Obviously this is not the complete name, so it might possible I miss some name. So if I will miss that name, so for that I have used this kind of word. Okay, so main contribution is started from the Utkin, Darkunov, Sartak, Sarah Spurgeon, Sarah Ramirez. So very nice books are written by this particular author, particularly for the nonlinear systems. Okay, and after that Go, Bartoszewicz and Professor Vigyan Bandyopadhyay is also contributing a lot towards the discrete sliding mode control, and due to their contribution, huge contribution in discrete sliding mode control, he become IEEE fellow in the same domain. Okay, so now implementation characterization. So control input computed only at the sampling instant, and after that control remains constant over the entire sampling period. Okay, so we will design control, and next sample again I am going to change the control, because everything is discrete in nature. So if you see the discrete sliding mode control, so in discrete sliding mode control basically we have two different school of thought. So what kind of schools of thought in case of discrete sliding mode control? So first is switching based. Okay, so what is meaning of switching based? We are taking the continuous sliding mode control, and after that we are going to discretize it. So after discretization again switching term is inside that discrete model, and due to that reason this Professor Gao has shown that if you are going to get some kind of reaching law, actually why I am talking about reaching law, because if you remember the foundation of continuous sliding mode control, so sliding mode control design has two steps. So first step is called reaching phase, and after that I have to slide along this particular line. Okay. So here during reaching phase I need some kind of discontinuous control, and discontinuous control has two responsibility. One is responsibility that is going to compensate the matched uncertainty, and second responsibility is to take any initial condition. If trajectory will start from any initial condition throughout this space, then in finite time I have to move to the sliding surface. That is another responsibility. Okay. So in order to move here in finite time, some high switching frequency is required, and after that I have to maintain along this line. So this is also very, very important. So in order to maintain here, we have to switch with very, very high switching frequency. Now during the discretization process, again since I have to remain in the vicinity of sliding surface, and if you are going to discretize, then again similar kind of requirement comes into picture. In continuous control, we have actually control at each and every time, and due to that reason ideally theoretically we can able to show that trajectory will converge from any point, and after that they can maintain, exactly they can maintain. But whenever sampling comes into picture, then this kind of behavior comes into picture, that is called quasi sliding mode behavior. So we will characterize that kind of behavior in the next subsequent slides. So another philosophy that is also very beautiful, and what is suggestion, since sliding mode control required some kind of discontinuous control, in case of the continuous you have already seen that in case of higher order sliding mode control, discontinuity is going to shift on the higher derivative. But if you see the discrete time system, that is inherently discrete or inherently discontinuous. So if inherently discontinuous, then it is possible that without using the discontinuous control I can able to achieve the sliding in absence of the disturbance. Okay. And that kind of approach is basically proposed by Bartoszewicz and Bartoloni. So what is main philosophy, that using one sample you can converge here, and after that you can maintain. Later this one sample theory is actually extended for the multiple samples. Okay. So that kind of things we are going to discuss in this particular lecture. And again design. So design step is exactly same like the continuous, if we are going to talk about the sliding phase. Okay. So this phase is called sliding and this phase is called reaching. So obviously I have already told you that reaching phase in case of the discrete time sliding mode control can be continuous or discontinuous both, and due to that reason reaching phase is particularly different for the discrete prospect. So how basically we are designing a stable sliding surface? First step, we are assuming that ideal sliding comes into picture. What is meaning of ideal sliding? Whatever sliding manifold we are designing, so we are going to make sure that sliding manifold equal to 0 in some finite time. Okay. And after that, even if that is not exactly 0, but we are going to remain on the very close vicinity of the sliding surface after finite time. Okay. And obviously once we are in the close vicinity of the sliding surface, at that time we have reduced order dynamics. Okay. And that is nothing but some kind of zero dynamics. So that dynamics should be stable by the design. Okay. So always we have design parameter. So we are going to choose the design parameter in such a way such that whatever sliding phase dynamics, that should be stable. I have already discussed that basically reaching phase is little bit different, because we can able to achieve this with lower switching frequency, because in discrete time case we have always restriction of the sampling time. So I cannot able to force sliding with very high using very high switching frequency, and due to that reason we have always compromise of the switching frequency. And obviously reaching conditions are more complex because we don't have control at each and every place. We have just control at the sampling instant, and due to that reason theory of the discrete time sliding mode control is different from the continuous one. Now in case of the continuous sliding mode control, you might have seen that one of the fundamental law that is based on discontinuity, that is expressed like this. So this is reaching law, and what this reaching law is suggesting that if you have some manifold and if you start from any initial condition, then in finite time you can able to move. Okay, so how to move in finite time, or at least how you can able to attract towards this manifold. So for that we are maintaining SS dot less than equal to 0, and that is also justified from the Newton's law. Suppose that if S belongs to R, one dimensional manifold, so that is represented by real line, and if you have to move towards S equal to 0, that is equilibrium. So if S equal to 0, then S dot must be less than 0. Similarly, if you are here and S less than 0, then X dot should be greater than 0, because object finally is going to move in direction of the rate of change. That is the philosophy, and due to that reason in continuous time system, since I have control, so we are maintaining this kind of condition for the convergence, or this condition is also called the reaching condition, because I have to design first reaching phase. So this particular Russian scientist, what they have done, they have just created the equivalent of S dot. So what is equivalent of S dot? That is x k plus 1 minus s k, and sampling is 1, k plus 1 minus k 1. So using that they have actually replaced. So that is not exactly replacement. Otherwise, if we want to do exact means replacement, then we have to do s k plus h minus s k by h, limit h tending towards 0. So that kind of things we have to perform. Okay, but in discrete case always I have limitation of h is the sampling frequency, that is always finite, and due to that reason they have developed theory for the taking sampling equal to 1. Okay, so in this way basically this condition comes into picture, but it is possible to show that this will doesn't guarantee the convergence, and due to that reason this will only necessary condition, not a sufficient condition, but I have to actually develop some kind of necessary and sufficient condition, such that in discrete plane if I start anywhere, so after subsequent sampling I can able to reach to the sliding surface. So I am assuming that control is here, control is here, control is here, in between I can not able to update the control. So using this particular necessary condition we can able to give the direction of the momentum of the sk, but that will not guarantee the convergence, and after that Sharp-Tuck reaching law comes into picture, and you can see here what Sharp-Tuck law is suggesting, that if you see the xk plus 1 and xk, so xk plus 1 means next sampling state, whatever function s is sliding variable that is generated, so that is always less than the previous one, and it is possible to show that this is decomposed into two different condition. So necessary condition and this is the convergence condition. Okay, easily from here you can able to check that here and here these condition is always satisfied. Okay, so whenever we are designing sliding mode control, and if we use this kind of condition, then it is possible to show that if you start anywhere in discrete plane, so after subsequent time interval you can able to move towards the sliding surface. Now another reaching law that is proposed by the Fruta, and Fruta is very famous, he is one of the very great scientists from the Japan, and he has also created one kind of pendulum that is called Fruta pendulum, and for research purpose that is excellent setup. Okay, so now they have given one kind of Lyapunov based criteria such that you can able to attract towards the sliding manifold. Okay, and same alternative form he has actually generated. It is not difficult to show, from here one can easily able to get this. Now another reaching law, that is called Gauss reaching law. If you see the literature, most of time people are actually using this kind of reaching law. Why? Because this is very simple, and that is also the one can able to obtain by Euler discretization of the continuous reaching law algorithm. Okay, why this law is called reaching law? You can see that during the previous lectures I was talking about three different kind of reaching law. One reaching law, that is called constant rate reaching law, and second reaching law, that is constant plus proportional rate reaching law, and third one is somehow non-linear reaching law. Here alpha going to lie between 0 to 1. So these three reaching law we have used, and we are not actually appreciating this kind of reaching law in case of the continuous time system, because using this kind of reaching law it is not able to reject the matched uncertainty completely. Why? Because at s equal to 0, right hand side of this particular differential equation equal to 0, but we are preferring these two. So by discretizing the second law, that is proportional plus constant reaching law, so this is always give some kind of constant again, and due to that reason this is called proportional plus constant reaching law. And if you discretize by Euler discretization by taking sampling equal to 1, automatically by rearranging you can able to see that this expression comes into picture, where I have xk plus 1 and tau is nothing but the sampling time. Okay, so whatever sampling time you are going to take, but whatever sampling you are going to take, so in order to maintain discrete time stability, this extra condition comes into picture. In case of continuous, you can see that if there is no disturbance, then q and k, any positive number if you will take, then obviously this law comes into picture. Okay, and you are able to maintain s equal to 0 in all finite time t greater than equal to t. But here in discrete time case you cannot able to do that, because discrete system has inherent limitation, and due to that reason you have to maintain this between 0 to 1. Okay, it is not difficult to show this. Why? Because suppose that this term will not present. So how to maintain xk plus 1 in each next subsequent such that xk is tending towards 0. So for that, whatever value here, that is going to lie between 0 to 1. So based on that particular theory, this condition comes into picture. So what is attribute of this particular law? Trajectory move monotonically towards the switching plane. Switching plane is sk, and after that, once they will reach to this switching plane, then it is possible to show that this kind of action started. Okay, so basically I have cross and recross action started. So basically zigzag motion is actually started along this particular plane, and obviously we have non-increasing zigzag amplitude and trajectory stay with a specified band. It is possible to show that as time is going to pass, so initially this zigzag motion amplitude is very high, finally that is going to become smaller, and always that is going to lie actually in the very close vicinity of this sk. Obviously we cannot able to ensure that sk is perfectly 0, and due to that reason some special band come into picture, and that kind of sliding mode control is called quasi sliding mode control. So basically quasi word is used because there is no real sliding. Okay, no ideal sliding. So in case of the discrete time system, if we use the discretization of this law, proportional and constant rate reaching law, then obviously we will get this law, and this has beautiful property, monotonicity property. It means that monotonically we are going to decrease to the sliding surface. Okay, and obviously I will actually finally converge to the invariant set. Okay, so once I will start from that set, I am not going to actually deviate from that set, and that is somehow form a bond that is called quasi sliding mode bond. So I will show how basically quasi sliding mode bond will obtain after actually implementing this kind of control that is developed by the discretization of continuous one. So I am going to start with discrete time system. Okay, so these kind of discrete time system you can able to obtain in two different way. So some systems are inherently discrete in nature, then obviously you will get this model. but most of the system is continuous, then you can discretize it and then you will get this model. And after that, now again you can design sliding surface exactly same like the continuous time system. And how to obtain the control? What you can do, if you will put xk plus 1 equal to 0 or xk plus 1 if you will calculate not equal to 0. So now I have this kind of system comes into picture in next instant, and where I am going to substitute xk plus 1 from the upper equation or from the system equation, discrete system equation, and then what is our goal? Our final goal to match this equation with this equation, and during this matching whatever extra term that comes into picture, that I am going to interpret as a control action. So I hope that easily you can able to design control whenever some sliding surface is given to you. So this become basically phi tau xk, and after that tau 2 tau uk, and finally what you have to do, now you have to apply this kind of algorithm. So 1 minus q tau and xk, and after that next term is actually k tau into signum xk. Now just you can equate, okay, and by equating you can easily able to calculate the u. Okay, now during this process I am assuming that by design this should be invertible. Now how to actually calculate the bond? So we have already seen that if you start anywhere monotonically I am going to decrease, and after that now I am going to cross and recross. So xk plus 1, and if you see the sign of the next, so xk plus 1, and after that I have xk and then xk plus 1. So in order to maintain or in order to get some kind of band, cross and recross comes into picture. Okay, so if this side, because whenever we are designing manifold, so by designing manifold, and if uk belongs to R, if I have just one dimensional control, so this whole plane is separated into two parts. So one part xk greater than 0, another part xk less than 0. Okay, so suppose that xk k1, if you are in this part, so next instant in order to maintain this kind of cross and recross, second part should be positive. So I am assuming xk plus 1 is positive, then next previous one minus xk, that should be less than 0. Okay, and obviously what is our assumption? Our pre-assumption is that all subsequent step should decrease such that I can able to maintain inside the bond, and due to that reason we have used this kind of inequality, and if you rearrange this inequality, then approximate bond you can able to calculate like this. Okay, and this bond is called quasi sliding mode bond. So whatever law I have discussed, so this is based on the discretization of continuous. Another one that is just based on linear reaching law. So what is justification of this? Since we know in case of discrete time system I never need and I never able to achieve the exact sliding, most of time I will get the quasi sliding. Due to that reason, now this using this linear reaching law, where theta is nothing but some kind of diagonal entry, where all diagonal entry is positive, then and going to lie between 0 and 1, because why we are assuming that is 0 and 1, easily you can able to see from the stability theory that if I have this kind of expression and if lambda lie between 0 to 1, then finally whatever xk that comes into picture, that is lambda k into s0, and due to that reason we are restricting whatever diagonal element, such that this whole reaching law for nth order system or mth order system, that is actually decoupled into m difference equations. Okay, now one of the reaching law that is called Utkin's reaching law, that is a special case of the above reaching law, and what that is suggesting that in one sampling instant you can directly converge here, and after that you can maintain. Okay, so again if xk plus 1 equal to 0, then obviously in just one sampling instant I can able to converge to the equilibrium point. But in this particular process huge control is required, because in one step you are very far from the equilibrium point, and you have, or equilibrium point here is nothing but the whole sliding surface. So in one step you have to actually reach to the sliding surface. Okay, so this is not a easy task. Huge control is required in this particular process. And now again several system. Whenever we are talking about discrete time system and sliding mode, it means that I am talking about the disturbance. Okay, and disturbance we are assuming that is bounded, and again I can able to design this sliding surface, and xk plus 1 I can able to do, and then I will design the control. And how to design control I have already told you. Just you can actually equate both side. Xk plus 1 you can replace by the reaching law that is proposed by the Gauss, and during that process you can see that one disturbance terms comes into picture if you are going to equate. Okay, and since control containing the disturbance term, and due to that reason we cannot able to implement that kind of control. Okay, so if disturbance free, then easily you can able to implement the Gauss reaching law, but if disturbance comes into picture, then you can not able to implement due to the reason because d tilde k is not known to us, and due to that reason we have to assume something. So we are assuming that disturbance is match, and after that we are assuming that disturbance is bounded, and d0 is the mean of disturbance, and d1 is nothing but the spread of the disturbance. And then it is possible to show that if you modify the reaching law, okay, you can see here this is the disturbance term, and this is justified because in continuous time system also whatever discontinuous control we are proposing, always we are proposing like this, and we are telling that in presence of this unknown disturbance, unknown bounded disturbance, s equal to 0 in finite time. Similarly, here whatever reaching law I have proposed, so that is going to contain some kind of unknown disturbance dk, and what is d0? d0 is the mean of the maximum and minimum defined exactly here, and in this way I can able to ensure the convergence condition. Okay, and where dk is nothing but C transpose is the design matrix. So I have to design C transpose in such a way such that I can able to minimize this disturbance. Okay, so based on disturbance you have to select some value of Ck. So that is again design problem. And now you can see that inside the control everything is actually known. D0 is known because what is D0? That is the mean of disturbance. I am assuming that upper bond and lower bond of the disturbance is known, and D1 is also known. Okay, and after that, in order to maintain quasi sliding mode control, I have already told you that we have to do cross and recross. Okay, so I have interval xk. After that, whatever xk plus 1, their sign should be negative, and whatever xk plus 2 comes into picture, that should be positive. So suppose this is xk, then second instant become xk plus 1, third instant become xk plus 2. So if this is positive, then this should be negative, then this should be again positive, and due to that reason this requirement comes into picture in order to hold the quasi sliding mode. Okay, and based on that one can easily able to calculate the bond by proposing this kind of law where disturbance is also included. Okay, so we have calculated xk plus 2, so easily one can able to calculate xk plus 2, and after that substitute whatever term inside xk plus 1, then we can able to get this kind of expression, and we know that what is xk plus 1. So from here if you substitute and if you maintain this signum xk plus 2 equal to signum xk, because what I have told that whatever sign here, same sign that is going to maintain. So if you are going to substitute that, then finally I will get this kind of bond. Okay, so now modified quasi sliding mode bond can obtain like this. So please check it. Okay, so whenever we are going to modify the reaching law, it is possible to show that in absence of the disturbance I have some bond. Now in presence of the disturbance I have this kind of bond comes into picture, and by substituting d1 I can finally able to show that this kind of bond comes into picture. Okay, so by designing tau very small, I can able to reduce this bond, and it is also not difficult to check that if this is converted into continuous time system tau equal to 0, then whatever bond come into picture, that is 0. So this is more practical, maintain robustness property, and obviously not a true sliding mode control comes into picture, and inherent chattering, because during the proof only we have applied the methodology such that cross and recross occur, and due to that reason I cannot able to stop the chattering. So what is origin of chattering? Because we have just discretized the continuous sliding mode control. and control cannot change continuously, because always I have some kind of sampling restriction and inherent chattering comes into picture. And due to that is a next approach that is comes into picture, that is called the without switching. And what is main idea? You can keep xk plus 1 equal to 0 with xk not equal to 0. So that kind of concept is actually driven by deadbeat control. So what is basic idea of deadbeat control? So directly you can converge to the origin, okay, in one step. So similarly, now we are not going to converge to the equilibrium point. What basically we are going to do? We are going to converge to some manifold, and after that subsequently we will move to the equilibrium point. So in that particular way, deadbeat controller is different from the sliding mode controller. Now again, what I have done? I have taken the LTI system. So continuous LTI system I have taken, and after that we have performed the discretization. So this is the equivalence between continuous and discrete time systems, and after that you can see that we have designed the control law, and this control law is very easy. What you have to do? You have to just keep xk plus 1 equal to 0, and then whatever control comes into picture, that you have to calculate. Now it is possible to show that once you apply this kind of control, okay, so this particular control, since we have to reach in one step, and due to that reason most of time actuator saturation comes into picture, and due to that reason now it is possible to show that one can able to modify the control. So that modification is suggested by Professor Utkin, that if this is the saturation limit of your actuator. So if equivalent control is less than your actuator saturation limit, then you can apply this. Otherwise just you can give the direction. So this is nothing but unit vector based control. Okay, so this is just going to give the direction, and every time I am going to utilize the maximum saturation limit of the actuator. And obviously we have this, then I have to apply this control, and I have to show that norm of xk plus 1 that is less than xk. So that kind of things we have to show. So this is the convergence condition, and if we are able to maintain this kind of convergence condition, then it is possible to show that xk is less than equal to xk norm of this. So this is Sharp-Tuck reaching law. Similarly, if I have disturbance, then it is possible to show that, again I am assuming that disturbance is mesh disturbance, and in framework of mesh disturbance system is written like this, and this is the sliding variable. And now whenever you are going to maintain xk plus 1 equal to 0, then obviously again control is going to contain some kind of uncertainty, and due to that reason again this control is not implementable, and due to that reason we have to modify it. Okay, and after modification of the reaching law, it is possible to show that again I can able to maintain the modified reaching law, where d0 and d1 is the spread and mean, and then finally one can able to propose this kind of law based on the disturbance. So here xk plus 1 not exactly 0, but we are in the vicinity of the quasi sliding, things are exactly like quasi sliding mode, and we are going to convert to the vicinity of the sliding surface, and control can be given like this. Okay, last reaching law that is proposed by the Professor Bartoszewicz, and somehow this is adaptive in nature. So they have actually added some extra term SDK, and in order to design SDK you have to satisfy this kind of condition. So in this particular slide I am not going to give the proof, but you can able to check the paper that is written by Bartoszewicz. Okay, and after that it is possible to show that SDK should satisfy this kind of condition, and we have to maintain SDK condition such that, because SDK minus SD0 initial and next sampling instant k, that is always greater than 0. So it is possible to show that SDK actually monotonically converge, and each step that is going to decay by this, and if this is less than 2 decay, then exactly equivalent to the Utkin's law. Okay, so again quasi sliding mode control comes into picture, and using this much step you can able to approach to the quasi sliding mode band, and after that it is possible to show that control one can able to obtain like this, and SDK is given like this, okay, and XK is always less than the D1, and this is the plot of that. So now it is time to conclude this lecture. So what we have seen? We have seen the comprehensive analysis of discrete sliding mode control. We have actually developed several modified reaching law for the robustness purpose, because we have our main goal to compensate the uncertainty. So exact compensation of uncertainty one cannot able to achieve in discrete case. Why? Because control is only available at the discrete instant. Okay, we have also demonstrated the effect of chattering reduction with by the adjusting the value of gain as well as the tau. And how basically one can reduce the chattering? By replacing the discretized control by the Utkins control, means within continuous way or without any switching function I can able to reach to the sliding manifold. So these kind of things is very suitable for the industrial application, and obviously using this approach one can also able to minimize the control effort, and somehow this will give some kind of flexibility using the design process. So with this remark I am going to end this lecture. Thank you very much.